things, the other one will have to change in some way or be transferred to another object or something. So, classic example of this is the ice skater. You know, at the end of the ice skating, they spin around doing the thing where they like put their legs out like this, they spin around, and then they pull their arms in like this, and it looks like they spin faster and faster. And I always assumed that was an optical illusion, but it's not. They actually do spin faster and faster. They do it on purpose. I don't know how you do the spinning thing to begin with. I don't understand how that's even possible. Turns out ice skates are not a well understood problem. Like, we don't really understand how they work. Yeah. So there's a lot of things like, no, we understand how airplanes work. Ice skates are confusing. We don't understand how they work. Also, the shower curtain effect. You guys know the shower curtain effect? You know, in hotels, you know it's mainly in hotels. You turn on the shower and the curtain goes whoosh, and it billows inward as soon as you turn on the shower. Yeah, we're not really quite sure how that happens. People have theories that are contradictory. Yeah, there's not a ton of research being done on it, but that we don't really understand the limits well. Yes.
Well, I won a Nobel Prize for figuring out why they.
Probably not, but someone did get a Nobel Prize for it. All right, sorry, gotta move on. So when they stretch in, when they pull things in, it's the same mass going. They have the same mass total, but they are reducing the radius of their limbs, right? Which overall reduces R. But since angular momentum has to stay the same, if R goes down and mass stays the same, then velocity has to go up, so they start spinning faster. So that's a classic demonstration.
Can we spin something?
All right, you know what? I can't show you guys. You have like 3 minutes to do stuff.
Okay, wait. I have the thing with ice skates is that because you know like ice when water is frozen, it expands, which is freaking weird. So I thought the thing with ice skates is that the ice skates like put pressure in it and like melted a little bit, and that's why it's slippery, and that's why they work. Only. What do you mean? Why?
Basically, you're saying the ice skate is somehow being hot enough to melt all the ice.
No, because of the pressure, like of the weight of the person on the ice.
Pressure can't melt ice.
It's friction, Benji.
Yeah, like with the pressure and the friction working together.
Friction produces heat.
Yeah.
When friction produces heat, causing the ice to melt, which is water. Less friction, less heat. Therefore, it would be like. I don't know.
If you're trying to find a flaw in Eden's argument, it's not going to work.
There is a flaw in Eden's argument.
Then tell it, because you're apparently not doing a good job of doing so.
I'm focusing way too much on the black spot.
Deflecting the argument was not making
I'm
it
legitimately,
right.
what the spot on your right?
Alright, since you cannot create a valid argument against Eden's statement, you retract your former statement of Eden's being wrong.
I don't retract it, you just are treating it as non-existent, even though it is a bad argument.
You haven't said your argument yet.
I did. Water would friction with water is considerably less. You're saying that the friction with the water generated would be enough to continue heating the ice. You
have your blade, right? This is your blade. You're moving forward. There is a downward pressure of friction, and this is the ice. It turns to water somewhere in between, and this is still ice.
If that was
living
true, wait, let's Google it. Why aren't we Googling it?
I don't know. I was about to Google it myself.
What the fuck?
Slippery ice, pretty.
Okay, that was weird.
That's the answer. Right and wrong.
No.
Can I finish?
Okay.
The ice skates don't want the ice.
No, they don't. The pressure is.
The main thing about angular momentum is the vector, right? So it's an x, y, z component. Those refer to spinning in this direction, spinning in this direction, spinning in this direction, right? So the key to remember is that Lx, the angular momentum in the x direction, is conserved separately from Ly and Lz. In other words, each one is conserved independently. It's not like some weird total of them. Each component of angular momentum is conserved. So the way to demonstrate this is with a bike wheel. It's either so much fun. The reason bike wheels are fun is because they're actually pretty heavy out here, thus they actually have a good amount of angular momentum. They're pretty big, so you get good angular momentum with them. So tell me, what's the direction of angular momentum? Good. This way, right? You turn your fingers the way it's going, so that it's going this way. Good. All right, now, by convention, which direction do we call up?
What?
Why?
Away from the gravitational force.
If you're working on a sheet of paper, X, Y, and Z is up, right? So up is Z. All right, now, here's the thing to consider. Usually when you're dealing with stuff, the Earth absorbs all your angular momentum, just like it does your energy and momentum and stuff like that, right? The fact you're standing on Earth sort of sucks up all the leftover stuff, and you don't see the conservation laws. But if you have something that separates you rotationally from the Earth, which this is actually something that one of Mr. Lawrence's students, you don't know who that is, of course, one of an old teacher's students built out of a truck axle a long time ago. It works better than anything you can buy because it's a truck axle. It's made to handle, it's made to spin very smoothly over very heavy weights, right? So, of course it's slightly tilted. Okay. So what's my angular momentum right now? In the Z direction. What's the angular momentum in the Z direction right now? Approximately. Zero, that's right? In the Z direction, there's no rotation going on, right? So, if I isolate myself from the Earth, the angular momentum has to stay zero, right? The total angular momentum of the system has to remain zero. That's what conservation means, right? So, what happens then if I turn the bike wheel?
It's magic!
Sorry, I have to raise balance. What happens?
Magic.
Why do I spin? Because I turn it, it has now angular momentum in the Z direction. I turned it, right? And the total Z angular momentum has to be zero. So something else must pick up the opposite angular momentum. And what's that something else? Me, right? So I don't spin as fast as this wheel because I have a larger mass. Oh no, I just gave you a hint about my weight. I have a larger mass than this bike wheel, it's true. And so I don't spin as quickly, but I have the same angular momentum, the same angular momentum, right?
Yes.
In fact, you can do this even better. You start like this, it actually goes a little bit faster. And then you turn it upside down, right?
Wowie.
Will we get to do this?
No.
Oh.
No, this thing has got like big spiky metal bits, and there's liability issues. So, look at the spiky metal bits sticking out there.
Wait a second.
If you fell on them, they would hurt a lot. Okay, bike wheels are awesome.
Weighs it down.
Why does a bike stay up?
I don't want to know.
You ever wondered how a bike works? It always depends on speed, right? You cannot balance on a stationary bike. I don't know, maybe you can if you're really good. But like basically you can't balance on a stationary bike. It has to be moving, right? Why does it have to be moving? Because when it's moving, then it has what? It has angular momentum and it wants to keep it. Now it's possible to transfer its angular momentum into something else, but it's not easy if there's nothing rotational around, right? So whenever you try and move it, it fights against you. And even when it's not on the ground, you can feel it fighting against any change in its motion. That's because it's basically trying to maintain the angular momentum, or rather, it's very difficult to transfer the angular momentum anywhere else. So the rotation of the bike wheel is what keeps it from falling over, because it has a tendency to stay up to keep the angular momentum in the same direction it is. Bike wheels are awesome, and this has nothing to do with this class, but then if you have a string on it, you can do this.
What?
Which is really cool.
Wow.
That's called procession. You'll learn on ModPhys. All right, so.
Can I take a video?
In fact, you'll learn on ModPhys in like a day or two, if I recall. We're just about to start angular momentum, I believe. Okay, so you see why I had to show you that? There's actually a cool picture. I wonder if someone's a video of it. There's a cool picture of someone skiing, except instead of holding poles, he's holding a bike wheel, a spinning bike wheel. Because whenever you push this way, it fights against you, so it pulls the rest of your body the opposite direction. So you can use it instead of poles to steer down the slope.
Well, yeah, but you have to keep it spinning.
As long as it stays spinning. But these are actually very good friction. They'll stay spinning quite a while. All right, so that's angular momentum, and it's awesome. Now, now for the fun part, quantum mechanics. So, now let's talk about quantum angular momentum.
What is quantum angular momentum?
What's a great
Even
question?
more
Well,
fun.
Same thing as regular angular momentum. It's defined the same way. It's not relativistic and all that, right? So it's defined the same way, ish.
As with
yes.
everything in quantum.
Is there relativistic angular momentum?
I asked that last
Benji,
period.
stop.
We try not to think about it. It would have to be. I've never actually looked into it. I'm sure I'll look into this.
It's time to stop.
Probably find some paper someone wrote online though. But, okay, here's the thing about angular momentum in the quantum world. Here's what we discovered about angular momentum. What are the units of angular momentum? Well, look at it. What are the units of angular momentum? Kilograms, meters per second, meters, so meters squared per second. Right? Kilogram meters squared per second, that's the unit of angular momentum. There is no shortcut to saying that. That's just the thing. Although it's very close to another unit. What's the unit does it look like? It looks like a joule. What's a joule? One joule is a kilogram meter squared per second squared. Right? Mass times velocity squared, right? So it's very close. So that means this thing is really the same as what? A joule times a second, right? That unit look familiar at all? We've seen it before.
No.
Yes, we have. Yes, we have.
No.
Well, what we discover in quantum mechanics is that angular momentum is, go ahead, guess.
Oh no.
Momentum.
It's not relative. It's quantum mechanics, so it's
Frustrating.
quantized.
Oh, wow. Who could
Like
have thought?
what? That means you can only have certain units of angular momentum. You can have 1 unit of angular momentum, 2 units of angular momentum, 3 units, but never 2.5 units. So your rotationness, your spinniness is quantized. And you're like, that doesn't make the tiniest bit of sense, Dr. Doc. And I'm like,
Okay.
so, and not only is it quantized, what are the units of this quantization? You can guess, not units, I mean, what's the smallest quantized unit you can get, right? The integer multiples of this thing. Well, you can maybe take, did you say 0?
Yes.
You can take a guess just by looking at the units of angular momentum. What's a small number that has that units? EV is energy. Planck's constant has those units. Well, it turns out that, remember I told you that h for Planck's constant is not really the fundamental quantity, and that most of the time we use the other one that we call h bar. Well, it turns out that angular momentum is quantized in units of h bar. That's why h bar is the more fundamental quantity, because it is the fundamental unit of angular momentum. So the spinniness of an object. Its angular momentum can be h bar, 2h bar, 3h bar, 4h bar, but never 2.5h bar. Yes.
So we talked about spin?
No.
We were getting there, one thing at a time. Okay. So angular momentum is quantized in units of h bar. Heat. Okay. Well, that's a little weird. But okay, now the good news is, how big is h bar in SI units? Really small, right? 10 to the negative 34, about 10 to the negative 34. So that's really small. So while angular momentum is quantized, it's in very, very small units. So it's not a big deal for most of us. Okay, good. Now something else weird. You have 3 different kinds of angular momentum, right? Now, in quantum mechanics, these 3 angular momentum as a measurement corresponds to, is not a number, it's a what? No, I mean, yes, you have a wave function, but the measurable thing corresponds to, and the measurable quantity itself corresponds to an operator, right? Remember that? And then, yes, then you can measure different eigenvalues on that operator. Do you want a chair, Michael? We got chairs. Okay, so angular momentum. So that means you have operators of angular momentum, right? Remember those operators? Okay. You in fact have 3 operators, Lx, Ly, and Lz. They're different operators because they focus on things in different directions, right? All right, good. Now for the fun part. Lx and Ly, the operators. Go ahead, guess.
Do not equal LZ.
Do not commute.
Oh boy.
Lx and Lz also don't commute. Ly and Lz don't commute. That has to be true, because as far as we know, there's no like preferred direction, right? So if it's true in one direction, it has to be true in all directions. So, what does it mean that Lx and Ly don't commute, and also Lx and Lz don't commute? Go ahead.
Can we not know the angular momentum in any two directions?
That's good. You can only know the angular momentum in one direction at a time. So you can know the angular momentum in this direction, and then you can measure it in this direction, but then this direction of angular momentum is no longer known.
Does that mean it can change?
Well, yeah. That means it has changed. But it's conserved, you say, but that doesn't mean it can't change. It just means it has to be transferred to another object. But if that other object is also unmeasured, then that's not hard to do, right? So what you end up with, you can have a particle and you measure it this way, and you get angular momentum of h bar, and then you measure it this way, you get angular momentum of negative h bar. That's just the direction, right? Negative h bar, and then you measure this one again, and now it's 0, and you can measure this one again, right? And it changes every time you measure one of the other directions. You can only know at most one of the three quantities at a time, which makes it tricky, because that means you can never write out the angular momentum vector. Right? You can never write out the vector is, x, y, z. You can't. You only know one of them at a time. Huh. Well, you might say, well, that seems difficult to work with. Is there anything they do that does commute with angular momentum? And the answer is yes, there is something. We do have this operator that we call L squared. L squared is related to is inspired by the magnitude of the vector, and it looks like this: Lx squared plus Ly squared plus Lz squared. But keep in mind, these are not numbers; these are operators. What does Lx squared mean if Lx is an operator? Good. Raise your hand. Okay. Well, yeah, you can just do it twice, right? Operators in action. Lx squared is do it twice, right? So this is do Lx twice, add it to the result, do Ly twice, add that to the result, do Lz twice. Okay, so it's still an operator. But this overall operator, it turns out that L squared and Lx do commute. Yay, and then since that works, also Ly and Lz also commute. Okay. So we can basically know two pieces of information at once. We can know L squared, and we can know one of the three components. Lx, Ly, or Lz. Those two are allowed to know at the same time to commute. But, so people ask, what are some examples of operators that do commute? There you go. So you can know two bits of information about them, right? You can know the total, and L squared is basically the total angular momentum squared, right? So it's like the magnitude of the vector squared. And then Lx or Ly or Lz is an individual component. Yes, ma'am?
Does that mean we can't know all three at the same time?
That's correct.
No matter what we try.
No matter what. You can only know one of them and the total. And that's it. Does this make things complicated? A little, yeah. But it also makes things fun. I mean, you don't want the world to be boring, right? I don't want you guys to find physics class boring. I know some people think physics class is boring, so we try and keep it exciting.
Why are you making us confused?
So, what should you say? Oh, good. I'm glad. All right, so let's talk about these guys. First of all, we should pick one. We can only know one of these, right? So we should pick one to work with. Which one do you think we should pick? Just like as a default. Which one should we pick? No, of course not. Lz. You're like, why? Well, Lz is spinning in this way, which is actually the easiest thing to imagine spinning, right? It spins either this way or this way, right? So it's something spinning in a flat way. So that's actually Lz is a reasonable thing to do. Anyway, it's completely arbitrary, but we pick Lz. Everyone picks Lz. So let's talk about Lz. If you have an operator that we want to know about, what's the first thing we want to know about the operator? We want to know? It's eigen. In this case, let's talk about its eigenvalues, right? So let's talk about The eigenvalues. Well, the eigenvalues are the possible measured values, right? What are the possible measured values of angular momentum? I already told you.
H bar, 2H bar.
It could be H bar, 2H bar, 3H bar. It could also be negative H bar, negative 2H bar. Negative is just a sign change. It's just a direction change, right? And also 0. 0 is also fine. Okay. Sorry, dot. So all the positive or negative integers are 0. Basically any integer times H bar. So since this could be any integer times H bar, we can abbreviate this to make it a little bit easier by writing this as n times H bar, where n is a special number that we call a quantum number. So called because n has to be a what? An integer. Right? So m is an integer. The reason we do this is because what we usually do is we just look at m and then remember later on that we multiply by H bar to get the actual value. So that way we just focus on a number and we just do all the stuff in terms of that number m. And then when you actually want like the real value, then okay, it's actually m times H bar. Okay? So we spend most of our time looking at m, the quantum number. Now, let's talk. Now, the eigenstates are just eigenstates that go along with this, right? You can label them, you know, H bar, 2, H bar, 3. I mean, actually, usually label them 0, 1, 2, 3, just using the value of n to label the eigenstates. Now, let's talk about L squared. The eigenvalues of L squared are a little more complicated. Remember, L squared represents the total angular momentum squared. That's what L squared represents. That's what corresponds to, right? The total angular momentum squared. What are the eigenvalues? You might not guess them offhand. I'll give them to you. 0 is 1. It's got to be, since L squared, it's got to be in units of H bar squared, right? Because it's L squared. So you have 0, you get 2 H bar squared, 6 H bar squared, 12 H bar squared, 20 H bar squared, 30 H bar squared, 42 H bar squared. What's the general sequence here? What's the general pattern? It is that, but there's if you could write it in terms of like the nth term is.
It's mh squared.
No, mh squared would just be 4, 9, 16, 25, right? Those aren't 4, 9, 16, 25. It's not like that.
2 to m or 2 h squared.
With the n plus n.
You can see the pattern by
No, n squared minus n, right? Which is good. It's an n times n minus 1, right? Look. 2 times 1, 3 times 2, 4 times 3, 5 times 4, 6 times 5. Do you see? 7 times 6. So the way we generally write this, we generally use the number we use is we always use a lowercase l, which you have to write as cursive, or else it looks like a 1. So you write as cursive l. So this is l, and we do l times l. Oops, l times l minus. We usually do l times l plus 1. Yeah. H bar squared. We do l times l plus 1. L is also a quantum number, right? L again is an integer. And this one's very useful because L just goes 0, 1, 2, 3, 4. And that's a lot easier to remember than 0, 2, 6, 12, 20, right? So rather than try and remember these guys, we just follow along with L. L goes 0, 1, 2, 3, 4. And that lets us figure out these guys. Okay. So, these are the eigenvalues of the operators that we care about. And we virtually always focus on M and L until the last moment. Like until we actually need an answer with units, then we take M times H bar and L times L plus 1 times H bar squared. And if you ever want to find just the total angular momentum without the squared part, what do? Take the square root, right? It's easy enough to do. Yes, sir?
Does that mean that there's 2 different possible sets that have an eigenvalue of 0?
No, we're going to start with L equals 0. That's a good question. We're going to start with L equals 0. So L equals 0, this is 0. L equals 1, this gives you 2, and so forth. That's a good question. And L is not, L is going to be greater than or equal to 0. We don't bother going negative, because if you go negative, you'll get the same numbers in the limits, right? You'll get negative 1 times negative 2, which is still 2. Negative 2 times negative 3, which is still 6, and so forth. So we just have L be a non-negative integer. Now, there is, if you think about it, a restriction on M based on what L comes out to. And you see what it is? There's a restriction on LZ based on the total value of L squared. What's that?
It has to be positive.
What? No, there's based on the total value of L. Good. LZ cannot be greater than the total angular momentum, right? The total angular momentum includes LZ, so obviously LZ by itself cannot be any bigger than the total angular momentum, right? So that's going to put a restriction on M compared to the value of L. And the restriction is a pretty easy one. It turns out to be a really nice one. It turns out to be this. M is less than or equal to L. Absolute value of M is less than or equal to L. So, as a quick test, if L equals 2, for example, what are the possible values of M?
Negative between 1 and 0, 1 and 2.
Very good. All the integers between negative 2 and 2 inclusive, right? Those are the ones that satisfy this requirement. So you see, M is not really over an infinite number of things, right? For a given value of L, M can only be a few possible. That's your question? Some of you should be drawing a connection to something at some point. Right? Yeah, right. You take an advent, you've dealt with these quantum numbers before, but now we're doing it the real way. The lame chemistry way, yeah. So all the stuff I'm showing you, by the way, is not experimental. This is all derived. This is all derivable. Experiments matches very, very, very well with theoretical predictions, and but it's all something you can derive. Okay, good. All right, we're gonna make a great time. So only one thing left. That's good. Usually we waste more time, but we're not doing that this time. That's it.
We can. If you want to, we can.
You can waste time.
Yes, we can. That's still some fine.
So let's talk about something now. So you see it, you're like, wow, does this make any sense? No, it doesn't make sense. But the rules are very simple. Okay? For any given value of L, you have possible values of M. That would just have to be told to you. Information would have to be told to you. And for n, you can figure out what the actual number is by multiplying by h squared. For a given value of L, you can find the actual number by taking L times L plus 1 times h squared, right? Okay, now, let's talk about something interesting. This is the sun. This is the earth, not drawn to scale. Okay? Tell me, what is the axis of the angular momentum of the earth? What is the axis? You know, what's the center of the rotation of the angular axis of the angular momentum of the earth?
This was
Sure. What did you say, John? That was just kind of clockwise from the top. Actually, it's kind of fine. But where's the axis? Okay, so go through the sun. Is this?
Oh,
Yeah.
that's the sun.
That's the sun. Yes, that's the sun. It's only that.
So,
Okay, which is basically the sun. That's the slightly off. You can basically call it the sun. Okay, to the sun. Does someone have another argument? You hear a boy like this, it's not really an argument. Can you tell me what is that?
You also have the rotation of the Earth itself.
Good, or it could be the rotation around the North Pole. Isn't that also angular momentum? Is that also rotational motion? So, the Earth actually has two different kinds of rotational motion and two different kinds of angular momentum. One of them is that there's a North Pole here, and the Earth goes this way around the North Pole. Convenient trick. Earth always goes in the positive direction, even stick your thumb along the North Pole, the open system. And as long as you use your right hand, make sure to use your right hand. And, well, there's no real proper orientation to the sun, but we always, just to make it easier, we have the Earth go this way around the sun. So the Earth has two different kinds of rotational motion, right? We name these. This one we refer to as orbital motion for good reason, right? And we call this orbital angular momentum. Yeah. Are those really different? Well, let's ask this question. Let's say that a giant space goat comes by and bumps the Earth and knocks it out of its orbit, out of the solar system. Aside from the other things that would come as a result of that, would the Earth still have orbital angular momentum? Would it still have the orbital angular momentum that goes around the sun? If you knock it out of orbit, then it's not orbiting, right? So no longer has its orbital angular momentum. But is it still rotating on its axis? Assuming the goat didn't screw that up. Yes. So there's two different things going on here. One is the orbital motion of the Earth with reference to another point. You see that? But the other one is the rotation of the Earth without any reference to any external point. In other words, if we were trapped in a dust cloud, so we couldn't see anything in the sky, we would have no idea what our orbital angular momentum was, because we couldn't see anything, right? But we would still be able to see spin angular momentum, and we would still be rotating on our axis. And there are ways you could measure that. Yeah. I mean, sure you can, but if we were surrounded by dust, there's no way to tell how we're moving. If you're like a nebula, a dust cloud, then you have no way to tell how you're moving because you can't see any points. The dust blocks the night sky, you have nothing to see. Could you figure out your acceleration? You possibly could by looking at the dust, but you don't know how the dust is moving relative to you, so it's not that simple. Probably would eventually. But I'm just saying, if you can't see anything else, you can still tell. If there's nothing else in the universe, okay, the giant space goat eats up the rest of the universe, leaves the Earth behind, right? You have nothing to orbit around, but you can still keep spinning. Doesn't do a lot of good, but you could. Yes, Ben.
Do these values commute?
Are these values mute?
Commute.
Commute. An interesting question. Let's define them first, and then I'll answer your question. So this is called orbital angular momentum, and this is called spin angular momentum. One of them is an orbit around another point. The other one is a spin just around its own axis, not with reference to another point. Okay? That's the main thing. Orbital is about other objects, right? Whereas spin is all about itself only. Okay, Benji asked a good question. If you have two different types of orbital angular momentum, two different types of angular momentum, spin and orbital, do they commute? The answer is I know you're all waiting for this.
The suspense.
Yes.
Oh.
They commute. So that's good. All it means is you have to account for both of these. Now, here's the thing. The Earth is, as you are probably aware, a fairly large object. It is pretty clear what a spinning Earth means. If you imagine a marble, you guys know what marbles are?
Yes.
You know, anyone play marbles?
Yes.
Wow, is this like some hipster retro thing or what? And there's nothing wrong with it. It's kind of amazing.
They were pretty.
I assume they will be able to. How about jacks?
I was a
Play
child.
jacks? Wow. Okay.
I can swallow them.
Rich?
Never mind.
Rich is actually really funny. It's actually really funny. Anyway, what, euchre, gin rummy?
You're all such nerds.
I mean, it's an old game, but it's a different play.
It is not an
Bridge is actually, I mean, you can play Bridge is a very complex game and actually very fun. Yeah, it's complicated. But the rules aren't that complex. It's just really hard to figure out how to play. So, all right, sorry. Moving on. No longer doing great on time. That's fine. We actually don't have a lot to cover. So they can be. That's all good. Why they? Oh yeah. So marble spinning. It's easy to figure out what a marble spinning is. Okay. An atom spinning. Yeah, you could visualize that, right? But tell me, what does an electron spinning look like? As far as we know, how have we been treating electrons? As far as we know, we treat them as points. Can you have a point spin? But here's the thing. Imagine I'm holding an electron.
Oh boy.
Imagine I'm holding an electron. And imagine I have one of these guys. Okay? What could I do?
You would
Right? I could, holding the electron, well, here, let's imagine this way. Let's say that you have a bike wheel, you know you have a bike wheel that's spinning, locked inside like a lead briefcase that cannot be penetrated in any way. So, you know, people do this sometimes. And you want to know, now, there's a lot you cannot measure about this. You cannot measure the mass of the bike wheel. It's probably dwarfed by the mass of the lead, right? You cannot measure the speed at which the bike wheel is turning because you have no way of measuring that. Okay? You cannot measure the radius of the bike wheel. You can't. It's a big thing. Well, what can you measure about it? You can measure angular momentum. How? You stand on this, turn the box, right? And if you start spinning, then there's angular momentum. And you can measure how much by measuring your own mass and so forth. You can figure out how much angular momentum there is, right? So you can measure angular momentum without measuring any of the subcomponents of it. Okay, so true story. This is not how you actually do it, but if you imagine holding an electron, you stand on top of this, you turn the electron. Okay, this is accidental, so the floor is slightly tilted. But anyway, you turn the electron and you start to spin. That is to say, electrons have angular momentum. It is not clear that electrons have a radius or a velocity, or like those. It's not clear what the thing looks like. You know, their electrons are too small to see. But what we do know is that they have angular momentum. Yeah.
How do you know if it's like spinning or how do you know?
Well, in this case, it'd be spin because you're just holding it, right? So there's no other reference point for orbit around. So, so here's the weird thing. Not just what? No, the electric field actually is not when it spins. Actually, yeah, it turns out to be invariant. So, no, that's actually predicted. That's actually a sensible behavior because the actual distribution of charge does not change. Therefore, the electric field does not change. So what we discover is not just electrons, but all particles have an intrinsic angular momentum that is called spin. What's the word intrinsic mean? It is a property of the object. If it didn't have it, the object would not be that object. For example, electrons are negatively charged. If you see a positively charged electron, you don't call it an electron.
It's positive.
Yeah, for example, right? But you don't say, "Oh, look at that positively charged electron." You know, humans have two eyes. I'm not trying to make weird attacks on weird senses of population. Like humans have two eyes. Fair general statement, right? If you meet some thing that looks kind of like human, but with like 5 eyes instead, like 3 on the head and 1 in each palm, then like you don't say, "Oh, that's an unusual human," right? That part of it's intrinsic to humanity to have 2 eyes. You can lose one, right? But like you have them to begin with, right? Basically. So that's what intrinsic means. If it's different, you don't call it the same particle. It's part of the particle. Now, when we say the spin and orbital momentum, that means we have a whole bunch of operators to consider now. Now we have the orbital operators, which are L, Z, and L squared. Those are the orbital operators. And now we have spin operators. Since they commute, we can use them, right? And those operators we'll call SZ and S squared. S for spin, right? And here's the rule. Spin follows there's one exception for spin only, except spin can be half integer. Why? The answer to the why is far, far, far too complicated. So, I have not been able to find any kind of shortcut, simple, hand-wavy way to describe it. You do a lot of math, and then you find this answer. That's how it works. Yeah, pretty good answer, huh? Yeah. Yeah, no, I have not found a way that, I mean, I can explain it to you, but it would need a semester or so. So, I covered that in my quantum mechanics independent study. We actually showed this in like early May. That's how long it takes to get to it. So it's not a simple thing you can just say, and you can just prove, show, or even argue, but it's the truth. So each of these guys is a corresponding quantum number. This one is n, and this one is l, right? So these guys need quantum numbers too. We call them n sub s and l sub s. Why is that terrible? These are n and l for the orbital momentum. These are n and l for the spin. If you call them like q and p, it would be even more confusing, I think. Yeah.
Whenever you're spinning a bike wheel, is that orbital or spin?
You're spinning a what?
Whenever you're rotating a bike wheel, is that orbital, the end of the bike wheel orbiting around the center, or is it spin?
For our purposes, we're going to call it spin. Okay? It's true, you can say, oh, but it's really these things orbiting around the center, right? Yeah. But here's the thing. You can always take, you can say, look, the Earth is just a bunch of particles orbiting around the central point, right? And you'd be correct. But for an electron, that appears to not be so. For an electron, there is nothing to orbit around, but it still has angular momentum. It just does. So you're like, okay. So that means that spin can be half integer. So for example, you can have L sub s is allowed to equal 3/2, for example, as a half integer, right? The rule is, however, that the difference, if L sub s is a half integer, then all possible values are half integer. That is to say, the possible value of m sub s would be negative 3/2, negative 1/2, 1/2, 3/2. Okay? It would not be any of the ones in between. Similarly, if L sub s were 2, what would be the possible values of m sub s?
Negative 2, 1,
Negative 2, negative 1, 0, 1, 2. You see how it works? The rule is the difference between any m sub s still has to be an integer. That's really how it comes out. You're allowed to have half integers for spin, but if L sub s is a half integer, then all the m sub s must be half integer. If L sub s is an integer, all the m sub s have to be integer. Yeah?
Rule applies, so like if m sub s, half integer, and L sub s must be.
Well, yeah, it goes the other way too, of course. So you have all the same rules, it's just that, so spin and orbital, the orbital quantum numbers and spin quantum numbers are independent of each other. When I talk about the intrinsic quantity of spin, that's L sub s, okay? The spin of a particle is usually L sub s. So there's only 2 numbers that I ask you to memorize in this class, okay? And they are the spin of an electron is L sub s equals 1/2. And the spin of a photon is L sub s equals 1. Okay. Those 2 numbers I expect you to know. I think that's not too hard. So what are the possible m sub s values for an electron? Good, negative 1/2 and 1/2 are the possible m sub s values of an electron. Since there's only 2 possible outcomes, we often refer to them as, yes, there's only either negative 1/2 or positive 1/2, right? And negative 1/2 is spinning like this, and positive 1/2 is spinning like this. No. What?
Super simple.
We call these down and up. Spin down, and now that it works. Spin down, spin up. In fact, with eigenstates, we often write it like this, with arrows. Okay. So spin 1/2 particles have only 2 possible states, up and down. And so because of that, we often call them spin up, spin down. You hear that a lot. Okay? But when they say spin is a number, it's always referring to else if s. Yes, go ahead. I'm aware of that. Okay, good. I will post some homework because we don't have anything to do tomorrow, and the question is due Monday, so you should do the homework tonight, right? I will give you time to work tomorrow, but we should get the homework done before tomorrow.
I think we should all work tonight.